Hi everyone, welcome to my talk on bug-free JUCE UI. My name is Wilczek, and in this talk, I would like to share with you a way to think about GUI code to make it bug-free. And this talk applies both to app UIs and plugin UIs, and it should be, a kind of a proposal of how we could think about this problem in general. Here is a QR code and a link to the slides if you want to reference them later, and this slide will also be available at the very end. So, who is this talk for? Mostly, I would say it's for mid and senior developers working in JUCE, because the talk will draw heavily on JUCE concepts, but it will also be helpful to people just starting out in JUCE to kind of show the scope of what are the problems that appear. And finally, in a kind of a broader sense, it should be helpful to C++ developers who write GUIs. And just a few words about myself. My name is Wilczek. I'm an audio programming consultant and educator. So part of my professional life is writing code, and the other part is teaching audio programming. And to this end, I created the blog, thewolfson.com, and the associated YouTube channel, which I highly encourage you to subscribe to. I'm also the author of the DSP Pro online course on learning digital audio signal processing. Even if you don't have an engineering background, you don't have advanced math background, you don't know programming, that should help you transition somehow into this field of audio programming. And starting this year, I'm also an ADC mentor. And why did I want to give this talk? Well, as I said, I'm a teacher, so I see over and over again my students having problems, trying to structure their code properly. And this is especially important for GUI code. Apart from this, in my consulting experience this year, I worked on a mid-size app in JUCE that has a GUI. And what I found when I was looking through some, reference code on GitHub, there really isn't like a repository that would say, yeah, this is super clean, this is what I want to reference or I would like to follow in my own work. And some of the approaches that I used here, were successful not only in this app, but also in a plugin that I've been developing live with a live stream on YouTube. So I wanted to kind of create this talk as a reference point. So if someone would ask me what's my philosophy on writing JUCE GUIs, I could just point them into this single resource. So to get started, we need some definitions that we can use to have a common understanding of the problem. So the main definition that we need is a so-called model, which is a code representation of the domain we're working in. And in the case of audio, we could think that, the model consists, for example, of a preset of preferences class. It could be a synthesizer voice, right? So these are the entities, software representations of kind of real-world objects, and code that acts on these entities is called, use cases. And use cases kind of orchestrate how these entities collaborate. And model interacts typically with the outside world using so-called ports, but this is typically oblivious to the fact what these ports are, and model typically doesn't know that there is a GUI, there is a command line, etc. So we have our model, which is very high level, very abstract. But on the other end of the spectrum, we have a view, something what is very concrete. And this is the code responsible for showing the content of our application to the user. And in the JUCE framework, it's very easy to specify what is a view, because these are simply all the subclasses of the JUCE component. So in this talk, when I mentioned the word component, I specifically referred to subclasses of JUCE component, because component in software engineering has many different meanings. So let's just stick to this one. The next definition that we need is faking. So this is creating some fake dependency and injecting it into object we want to test during unit testing. And fakes are typically very simple. They just return the value and can replace cumbersome and complex operations like making a network request or a database request. And the last two definitions that we need is UI state and UI logic. When we're talking about the UI, we can think of it as consisting of states and transitions between these states. And UI state kind of captures a point in time that, how the UI looks at this point and how it will behave in response to user actions. And every interaction brings the UI to a new state. And what kind of joins these UI states is the UI logic, right? So we have our app in some state, the user clicks a button, and the UI logic performs some steps to calculate the next UI state. And so we can reason about UI in this form. So with these definitions out of the way, we arrive at the first problem. So how can we make our GUI code work as expected? And typically, when developers write GUI code, they should be asking themselves, like, is the correct value displayed, right? What if an error occurs? Is every possible interaction covered? And what happens if the app is resized? And the thing is that most of the time, like, the developers, they simply ignore the problem, right? They just, they say, this is fine. Like, this code probably works. So maybe I wanted to quickly have a survey of if you could log in to this, like under this QR code or the slido.com and with this code, and quickly, type in what are your strategies to handling this problem. Manual testing, okay. Test, so probably automated. Test like an end user, okay, great. Trial and error, ask the QA team. These are all valid approaches, right? QA manual testing, a back QA team. Unit testing, blind faith. That's a nice song by Dream Theater, by the way. Manual test for fingers crossed, verify the parameters are used during components. Automated, okay. Awesome. So yeah, being religious actually is one thing that Michael Feathers called in his approach, edit and pray, right? Because that's how we can summarize these concepts. So in edit and pray, which is a very popular approach, you focus really hard on the code and making the change, then you make the change and you pray that it's correct, right? That you didn't break anything. And kind of like an extension to this are manual tests when you compile your application and then you kind of poke around trying to see if everything works fine. Another development of this is having a QA testing team. And as I said last year in my talk on bug-free DSP code, QA testing is a little bit too late in the process. It's super useful, but we as software engineers, we want to have fast feedback. So that's not a valid approach if we are thinking about the general approach to writing GUIs. And then we can have these end-to-end GUI tests that somehow mimic user actions. And this is a very interesting approach. This is an example from Windows Presentation Foundation GUI framework. And in this end-to-end GUI test approach, we write some code. We use a specialized testing framework, and we write code that somehow mimics user actions. And here you can see it in action. We launch the application, we get the window, we find a button, we click the button, and then we can assert if a content of some text box change. And that actually has been done in JUCE already. If you look at a talk by Joe Knoll from 3 years ago, they did this to test their applications. And it works really nice. The thing is that they needed to build, oh, that's quite dark, but they needed to build quite a lot of stuff around to get this working. And as Joe Knoll pointed out, like GUI tests is not something, like this style GUI test is not something that you want to write in a big volume because they are slow to write, they are costly to maintain, they're slow to run, and they're also flaky, right? Which means often they can fail without a reason. Right? So you can run them once, they pass, you can run this twice, they fail, and you're never really sure what was the reason. So in this kind of unit testing pyramid that's very often shown, it shows how many tests of a particular kind there should be. So in general, they always say that manual tests should be avoided and the largest portion should be devoted to unit tests. Okay, but is there a better solution than having a big dedicated framework just to test the GUI? Isn't there something that is fast, that is standard C++, that doesn't require us to use a dedicated testing framework? We can use JUCE unit test, Google test, Catch2, etc. That we can easily assert all the desired effects and we can easily integrate it into our CI/CD integration. So that's our problem number 2, how to write automated GUI tests that are not in this end-to-end style. So one approach that I think is very interesting, and frankly, I'd be interested to see how it develops, is that with JUCE 8, we have access to WebView UIs. And for web views, so for web pages, we have established ways of testing them end-to-end, right? We have dedicated frameworks that allow us to interact with the DOM, make some backend calls, trigger JavaScript events, etc. But the thing is that majority of the code base is in traditional JUCE components, and probably this way of writing will still be used for the years to come. So what to do about this? And in my opinion, there are 3 main obstacles that prevent us from properly testing JUCE components. Let's take a look at a typical JUCE component. So here we have some component that has a button as its private member, and in the constructor, it sets the handler what happens on click. So we can already see that the stuff that happens here, cannot be easily invoked externally, right? Because this is private state of a component. We cannot just say, yeah, this button was clicked. There's an asterisk here because there's a caveat to this that probably you could abuse, iterating over children of a component and do some crazy dynamic casts. But I don't think this approach would be very maintainable. So let's look at another problem. A lot of code in components that I see is of this kind. So we have a component, it receives a value tree, so let's say a model, and then upon a click, upon user action, it directly manipulates this model. So the thing is here that to somehow test this, we need a fully fledged model, and then, yeah, we could assert this, but in a way, it's kind of mixing stuff together, right? We have our model, we have a view, and in this way, they are tightly interconnected. And if you think about this, like now components, it's not just responsible for the UI stuff, but it's also responsible for the model stuff. So it's definitely component is doing too much in this case. And here's another approach that's very popular. We have our component that implements value tree listener, and it listens to changes in the value tree. And again, we have a dependence of the view on the model. And the thing is that, again, if the text of the button changes, we cannot easily assert this. So in typical code bases that I see, JUCE components have a number of responsibilities. They hold the widgets, like the button, they hold the UI state, they position the widget, they paint additional stuff, right? They handle user actions, they manipulate the model, they observe the model for changes, they manipulate other components, and it just, we try to fit in so much into these poor component classes. I mean, like it seems to fit, right? But if you take a closer look, like something's not quite right. So like, what's the solution to this? And maybe one concept that helps us to think kind of out of the box to approach this problem is this concept that I encountered in this quite old book, but still somewhat accurate, Code Complete, which says program into your language, not in it. And let me read you a quote from the book that explains this concept. Don't limit your programming thinking only to the concepts that are supported automatically by your language. The best programmers think of what they want to do, and then they assess how to accomplish their objectives with the programming tools at their disposal. In other words, we use JUCE, we use C++, but we're not forced to, or we're not limited to just what they offer, right? We can always build our own tools. And you can think of it, for example, of the assert macro in C++. Like we have the assert, and it's nice to use it, but wouldn't it be nicer if assert did a number of other things that we think are useful? And nothing stands in the way of creating our own assert macro. Another example is this nice, progress bar in the slides. Like there is no feature in Google Slides that creates a progress bar for all the slides. But a few, AI prompts and some app script hacking allow you to create it automatically. And so the key takeaway here is that different languages and platforms teach us different concepts and tools. And so it turns out that a number of frameworks already solve the GUI problem. And the solution is the Model-View-ViewModel MVVM pattern, which has been used with much success in Windows Presentation Foundation, WinUI, Android, and probably a dozen of other frameworks. So in order to understand how it helps us solve the testability problem, let me show you a tour of GUI architectures so that we can understand where MVVM positions itself. So let's start with an architecture that I like to call put it all in the component that we really clearly saw. Yeah, it abbreviates to PITA. I think it's a nice description. And in short, the view, is tied very closely to the model. It manipulates it, it observes it, and contains everything that's not in the model. So more classically, there is the model view controller, MVC model, in which there's a controller that triggers use cases on the model, and the view passes user actions to the controller, and controller, it's typically said it selects a view to display. This is, very textbook definition, but I think it's hard to reason about this in the context of JUCE C++, but it makes sense, if we imagine the controller being a web server, right? Then a web server can return an HTML web page. That's our view, okay? But this is not very helpful, so maybe let's take a look at the model view presenter, MVP, also called the passive view. So here we have a presenter that contains UI logic, which triggers use cases and observes the model. And the presenter controls the view via an interface. And it manipulates the view and it injects the UI state. And the concrete implementation of the view passes user actions to the presenter. So this is already quite nice because we have the interface, so we can fake it in unit tests, right? So we can test the presenter by faking the view, creating a fake representation of the view, and let the presenter manipulate it. And on this fake view, we can then assert certain actions. We can, of course, test the model, and we assume that our concrete view is a humble object. What it is, I'll explain in a second, but it's not tested. And MVVM kind of takes this idea further. You can nicely see that in MVVM, all the dependencies are in the right direction. So we have, again, the model and the view model, which replaces the presenter. It triggers use cases on the model. It observes the model for changes. But now the view model contains both the UI logic and UI state. And the view is, very passive in that sense. It just, observes the view model for the UI state and just reacts to the changes. So the view model says the background should be blue, and the view model just observes and says, oh yeah, the background should be blue. Yeah, okay, I should change this. Yeah, right. In this kind of sense. And then the view changes user actions, takes user actions and passes it to view model, who can then perform necessary calculations. And in this setup, we test the view model, we test the model, and we leave, again, the view untested as this humble object. And what is a humble object? A humble object is a concept also introduced by Michael Feathers, when we have a class that's very difficult to test because of some problematic dependency. And this is exactly what we saw in the context of the component. So the idea is to take all the logic out of this object and leave this object just with the problematic dependency, make it humble, right? And not test this object, but test everything else. Test the logic that was within this object. So that's exactly how MVVM works, by taking the logic out of the view and testing the view model logic. So let's recap what we discussed so far. We want to make our UIs bug-free. So we said the best way to assert this is to unit test it. And then how to test JUCE component subclasses? Well, it's difficult without breaking the invariants or a lot of boilerplate code. So the idea is to separate the UI logic and state to a view model, make the JUCE component subclasses humble objects, and unit test just the view model. So if we take this approach, then there's problem number 3, and the final problem is how to use MVVM in C++ JUCE. And it turns out that all we need is to have the data binding. And the data binding is a more specialized term for the observer pattern that I'm sure most of you are familiar with, where you have an observer that simply publishes some changes, and all the observer, where you have the object that's observed that publishes some event, and the observers get notified. And the data binding in terms of the view model can look like this. Here we can see that, for example, in WinUI, we can specify directly the binding in our UI mockup by saying xbind. And here we just bind to this text block content property of the viewModel class. The viewModel class is just a simple C# class, but the view can directly bind to one of its public properties. So in C++, let's see how we can somehow mimic this. And, well, could we use JUCE cached value? And the thing is that cached value does not directly allow observing. And since it wraps a property inside our value tree, it exposes kind of too much from the model. I also think we cannot use right away a JUCE value because it allows observing. We get notifications when the value of changes, but it's dynamically typed and weakly typed. So we would always need to have some code around this to check the type of the update that we get. And also observing is quite unhandy because we need to implement the listener interface every time. So maybe let's not program in a language, but into a language. And so I came up with this observable property concept that held up really well. So this is a full implementation of the base class, but what's important here are the 2 public members that we can observe the property when we get and supply a callback there that gets triggered when its value changes, right? That's what we want. And we can also query directly what's the current value stored in the property. But note that in this base class, we cannot directly set the value. We can do it, however, in its child class, the mutable observable property. And we can do it in 2 ways. We can either have it compare, like is the new value different than the last one, or we can force the update, for example, if the comparison is costly, right? And this set will always change the value and notify the listeners that it changed. And a nice feature of this is that if the update comes from a background thread, in the view model, when it updates some UI state, and the view should update itself based on this change, it should be always performed on the GUI thread. So we can create a variant that now allows us to post the value, post the update to the GUI thread. And so the change will be performed on the GUI thread, and the view can safely rebuild itself without the data race. So how does it look in practice? Well, in practice, we would create some holder class that exposes an observable property by a reference, and then clients can observe this property by supplying a callback code, and then as you can see, we cannot directly set the value of the property, but if something happens, like here it's calling a public API, then when this property changes, this callback code gets executed. So, and the only one that knows that it's a mutable observable property is the holder of the class, but as you can see, it's private, so it's fine. And this is quite a bit of boilerplate, so we can shorten this using a nice macro. I know macros are typically considered evil, but in this case, I think it really simplifies the workflow. And this macro declares the public members and also the private mutable observable property, and the whole flow is the same as before. So I created this tiny utility library that is header only and is based on boost signals 2. Has the boost license to make it very simple to use with the rest, which is even more permissive than MIT. And if you want to contribute, I encourage this, and I would really like to get some expert feedback on this for sure. But the key part of this presentation is to look in at an actual example of how we can do this in practice, right? And here I took a classic example of plotting a filter's magnitude response that is always a part of every EQ plugin, right? Just as a note, this example, I removed here all the unnecessary snippets like, resized, some styling, etc. But the full example is available in the repo with slides. Okay, so let's start with the view model that is responsible for the part where we can change a filter's cutoff frequency. And for this, we declare an observable property, frequency slider value, right, is the UI state. And this is something that the view can observe for changes, but also it can influence it by calling the public view model function that notifying the view model that the user dragged the frequency slider. And here we initialize this member. And the nice thing is that we can pass to the view model the callback that should be called from the model when this frequency slider changes. So let's take a look at the view. The view holds the pointer to a view model via a unique pointer. It holds the connections, which on destruction automatically unsubscribe from the updates to the observable property. And it holds the widget itself, the frequency slider. So once we create the view with the slider, we can immediately set its value to what's in the view model. Then we do the typical JUCE thing, right? We just override the callback if the slider value changes, and then we just notify the view model, and we observe the view model if the frequency slider value changes. And this is all that the view does. So now we can take a look at our model. So this is some EQ filter, right? And it can have its cutoff frequency changed, and then it stores the new cutoff frequency and calculates the magnitude response. And as you can see, this nicely lends itself to having the observable property also in the model. So if we change the magnitude response, everyone who's observing this property will automatically get notified. And for this, we have a magnitude response plot view model that observes this magnitude response. As you can see, it also stores the connection here. And upon change of this magnitude response, it stores it and then updates the plot. But it's the source of change that comes from the model. But if the app resizes, the view can also notify the view model that bounds changed, and again, we can update the plot. And as you can see, an update plot, we post a value to the GUI thread with a new calculated magnitude response. But this is all done in the view model, not in the component. And the nice thing is that now the view can take this plot value and draw this in this very simple fashion, like no calculations here. This is pure just GUI code, right? It also stores the pointer to the view model and observes it here. And it sees that if the plot changes, it simply needs to repaint itself. And finally, as I said, if the bounds of the plot change, then also it notifies the view model. So that's how you wire this stuff. You create your model, and then you create your view to which you supply your view model. And to the view model, you just supply the callback that should be called if the cutoff frequency changes. And then you have your view that's responsible for plotting, to which you pass the view model responsible for calculating the plot. And to this, you just pass the observable property. So the flow is that if the user changes a frequency slider, the component notifies the view model notifies the model calculates the magnitude response and publishes it, which the view model responsible for plotting gets, it changes the magnitude response to magnitude response plot, and the component that's responsible for showing it on the screen, can repaint it. And that's how you can test this, right? You can create a magnitude response observable property, you pass it to your view model, and then you notify that the bounds change, you supply it whatever you want in your resolution, and then you can actually assert if the path that's calculated is correct. And as you can see, we didn't need the full model, right? And it's all nice, short, and clean, and it's very fast. So there's always a caveat, right? When we use some tool, it's not for free. So the thing here, you may consider some of the code that I just shown a little bit boilerplate, right? We need to store connections, we need to expose properties, and all the bindings must be established. Another caveat is that model and ViewModel must never forget to notify their observers, right? If they do this, then the whole flow is gone. Finally, as you said, we don't get this out of the box in C++. We need to write our own kind of observable property to have this data binding. And only time will tell how well it holds. But so far, I found it, very useful in my professional work. So let's do a quick recap. My point was that you can create bug-free JUCE UIs by unit testing them. And you can make them easily testable by leveraging the MVVM pattern. And if there's nothing you take from this talk, then please take just this idea of programming into your language, not in it. And we saw this on an example of an observable property and using a view model for a component. This is a quick recap of what MVVM is. We have model, which is high-level abstract, and the view model contains UI logic and UI state, and it triggers use cases on the model, and it observes the view model for changes. And completely separate from the model is the view that simply passes user actions to the view model and observes changes for the UI state if it should, repaint itself. And then the view itself is a humble object that we don't unit test. Here are some facts about the MVVM. It enables testability of the GUI by decoupling framework code from UI state and UI logic. The core of the MVVM is data binding that we can implement via observable property. And we can safely apply MVVM to JUCE UIs, making components humble classes or humble objects, and observing the view model for UI state changes and notifying the view model on user actions. And we can also use MVVM in multi-threaded environments via the use of live observable property, where the update to the UI state is postponed to the GUI thread. Here I listed some references that I used. And if you'd like to stay in touch, then please join my newsletter. It's a very nice and kind professional network of programmers and enthusiasts of audio programming. Here you can also get the slides. Subscribe to my YouTube channel if you haven't done so through this 30 minutes of the talk. And if you'd like to learn digital signal processing from scratch, I encourage you to check out my DSP Pro online course. Thank you for attending. I'd be happy to take your questions.